This is part 6 of Quick Precalculus Review for Calculus, also part 6 of a unit focusing on comparing and contrasting linear and exponential functions. I promise in the next video, part 7, we'll finally get to exponential functions. I want to finish off our main thoughts about linear functions in this video, and I want to focus in particular on what I call a qualitative analysis of graphs of families of linear functions as parameters change. What do I mean by that? A family of linear functions is a group of linear functions, a bunch of them. In fact, infinitely many. The parameters that are going to change are going to be the slope and the y-intercept. I want to make animations to help me do that, and I'm going to introduce one of my favorite Mathematica commands called manipulate, which can be used to make animations among other things. We'll continue using some other commands like plot, show, graphics, and line, the last two of which we saw in the last video, to illustrate these things. Before I get into that, a real quick bit of house cleaning that I want to do. Here was our population model, Austin, Texas. Here was our function down there. I want to show you that Mathematica can do this algebraic manipulations that we've done in the past, focusing on differences in function values to find changes in the outputs. If I type f of t plus delta t here, minus f of t, that can be represented in Mathematica's memory, and it can be calculated. And you get this output. You see it's not simplified. There's a simplifying command called simplify that I can embed this in, and it will simplify it. It will use the distributive property and simplify to this. It looks like it could have been simplified more, but it kept the 0 there for some reason. It did the same simplification that I did here, 31.7 times delta t. That's the little bit of housekeeping I wanted to do. I wanted to show you that in the last video, but I'm showing it to you now. Alright, we want to focus on essentially animating this general principle and understanding slopes and intercepts better. If f is a linear function, and in particular it's got this equation, then the change in y is proportional to the change in x. In fact, the slope, also called the rate of change, is the constant of proportionality between those quantities. We proved that in the last video. In this video we want to do a qualitative analysis of linear functions along with that fact. Okay, so first let's just make a basic plot of a basic example. Let's suppose we're considering the example where the function is, say, negative 2x plus 3. Let's just type the function in there without function notation inside the plotting command. That's the function I want to plot. Let's say over the window where x goes between, negative 10 to 10. Okay, so this kind of syntax is going to say x is going to go from negative 10 to 10. Let's pick a plot range. Doing this kind of thing, we'll do a plot range in the y direction, also going from negative 10 to 10. Let's make the graph a bit prettier. Maybe we'll make it magenta this time. Thick magenta. That's going to make a basic plot. There we have it. You can see the scales and the axes are not the same. That can be fixed with aspect ratio is another option. I don't think I've shown that to you before. Maybe I have. Arrow automatic, I believe, makes these scales the same. Yes, that looks the same. Let's label the axes as well. Axes label. Arrow x comma y in quotes inside a list. I like making those bigger. Okay, that looks pretty nice. Let me add one more thing in here before we get into the manipulate animation. I'm going to want to have some grid lines in here. And if I put grid lines automatic, it will put those grid lines that you see in there. I'd like more than what you see there. Kind of a fun way to make more grid lines, though this might be confusing, is to use the table command. I guess I'm going to use that command in here as well. If I type table I, comma, I goes negative 10 to 10, remember what table did. I showed this to you before. It creates lists of things. We created lists of points of function inputs and outputs before. This is going to create a list of numbers starting at negative 10 and going up to 10 in increments of 1 unit at a time. In fact, I can separate this out on another line and enter it to see that that's it's going to create. Instead of typing that all out, that's a quick trick to making sure that I get all those points in this spot here, because I want to have grid lines at all those values of x and all those values of y. Put a comma in here. There's going to be grid lines at all those values of x and the same values of y. I get a finer grid that looks like this. Looks like graph paper now. Okay? So that's kind of nice as well. Alright, let's put this inside a manipulate. I want to animate this now. So I'm going to embed the plotting command in a manipulate. Okay, square brackets around the plot, manipulate in front. You see a little red up arrow here that's indicating that the manipulate wants more input. It's hungry for more input, so I put a comma. What kind of input am I going to use? I'm going to use the slope. I'm going to call it m, and let's say m starts at -5 and goes up to +5. If I type this list like this, that is going to make an animation where m starts at -5 to +5. But if I enter this as is, there's not going to be any animation. Why not? It does look like there might be an animation, but nothing happens as I move this slider. And by the way, let me make m look bigger in that output. If I put a comma, label style, arrow large, that will make the slider label bigger like that. Nothing happens as m changes. Where's the animation? Well, the reason is you haven't put m in this spot anywhere. And m is the slope, so what I want to do is I want to replace this -2 slope with an m. Careful, if I do it like this, that's not quite right either. If I enter this, nothing will happen. Well, I don't even get a line, and nothing gets animated as m changes. The reason is because the m and x being next to each other makes Mathematica think that's one variable, one quantity, mx. You want to either put a space between the m and x to emphasize to Mathematica to multiply them, or as a default, just always put a star when you want to multiply two different quantities like that. Now we will get an animation that shows you how the slope changes. I can move the slider, I can play it. We get an animation of the graph as m changes. The fact that I've got the grid lines in there makes it nice to recall what the slope means. For example, if I make m be 2, just ignore the second graph there, you can see based on the grid lines that the slope is 2. Every time delta x is 1, every time you increase by x by 1 from here to here, say, delta y is 2. Y goes up by 2, delta y is 2. Rise over run is 2 over 1 is 2, or is 4 over 2 is 2, etc. Alright, if I have a slope of, say, -3, now every time x increases by 1, when delta x is 1, delta y is 3, for example. This point is x is 0, y is 3. If delta x is 1, then delta y is -3. If delta x is 2, then delta y is -6. So in all cases, the slope is -3. I can also add more to this animation. I can animate the y-intercept. For example, I can change this 3 to a b, and I can use a b instead of an m. Well, in addition to the m, copy and paste that, change this m to a b. I can have two sliders that I use to animate it. Both m and b can be changed here, and they can even be changed at the same time, and you can even play them to change at the same time. You can make them go faster, or maybe make m go fast and b go slow. So the slope is changing very fast, even though the y-intercept is changing pretty slowly now. Let me quick show you can also start m and b at different spots. For example, if I use m, comma 2 in here like this, that's going to start m at a value of 2. And if I put a b in here, comma -1, that'll start b at a value of -1. This is the syntax to start it at some other location before you animate. So now b is starting at -1 and instead of -5, and m is starting at 2 instead of -5 in this animation. But I can still play it. I can even run it backwards. For example, I can let m decrease in value. What's the qualitative analysis? Well, the basic qualitative analysis is if m is negative, then your graph decreases. Y goes down in value as x increases. As you move from left to right, y goes down. That's a decreasing graph. If the slope is positive, that's an increasing graph. As x increases, as x moves to the right, y goes up. And of course, a slope of 0, I hope you realize, is a horizontal line. Delta y is always 0, no matter what delta x is. This intercept can still be changed, but that's what's going to happen with the slope. Alright, that's a basic qualitative analysis of the slope. Of course, a basic qualitative analysis of the intercept is that when b is positive, your y-intercept is positive. When it's negative, it's below the x-axis down here. and when b is 0, your graph goes through the x-axis, and that's called a proportionality, in fact, between y and x. Alright, final thing to do in this video is I'd like to think about animating this idea that we had when we used graphics and line to create similar triangles that illustrated why the slope is constant for a line, because similar triangles are going to have the property that their shape is the same, their angles are the same, and because of that the ratio of corresponding sides is the same, and in particular rise over run is going to be the same. Let's animate that in here as well. I can use show, remember, to combine plots. I'm going to put a show around the plot command here. What I have here is the plot command right there. I'm going to show that with another plotting command, graphics, which I introduced you to last time. I'm going to make, say, a thick blue line, and I'm going to make the same kind of line I made before, except with this animation. I'm going to start at some point, I'm going to move to the right under some other point and go up to that other point, but I want to be able to animate that. Let's pick a fixed starting point. Let's say we pick the point -2 comma f of 2, where f is mx plus b. Let's do it as m times -2 plus b. So that is going to be my first point on the graph. Think about why that works. I'm going to go over to the right a certain amount, -2 plus delta x. Let's make delta x be our certain amount. That's going to be an animation parameter as well. I want to go under, I want to be in the same y coordinate, so I just copy and paste this part there. And then I want to go up to the graph. After that point, I want to put a -2 plus delta x and plug that quantity, -2 plus delta x, into the function here in place of x. So I get an m times, in parentheses, -2 plus delta x plus b. That should do it, I think. That's going to make a thick blue line that I can animate. One more thing to do is I need to put a delta x in here as an animation parameter outside the show, but still inside the manipulate. Delta x, let's start it at 0 and go up to 5, say. Alright, I think this is going to work. Let's hope. Alright, delta x is 0 here, so you don't see anything, but as I increase delta x, there we go, I get my triangle. It's always a right triangle, and in this case, since m and b are fixed, it's always it's always similar to itself. If I change m and b, it changes what the triangle looks like, at least if I change m, actually. I get triangles where the ratio of rise over run is different. If it looks like this, you think of the rise as being negative in that case, and so you take the opposite of the ratio of this side to this side to get a negative slope. So that's kind of a real quick introduction to how to use manipulate. I'll end the video by letting you just look at this code if you want to write it down.